This is question 3. Hydraulic efficiency of a Francis turbine can be written as this equation, where HL here is head of losses in turbine and HB here is the net head. If losses is minimum, the hydraulic efficiency will become maximum. So I hope you can understand this term. Define an expression of V equal to whirl velocity at outlet with maximum hydraulic efficiency means the losses is equal to 0 and total losses can be expressed as this one. So for reaction turbine, head loss of relative velocity is 5% and head loss at draft tube is 20%. So velocity of flow is constant, which is 7.5 meter per second. U2 is 15 meter per second. At maximum efficiency, the net head is 90 meters. That means the whirl velocity at outlet, the guide vane at outlet, the blade angle at outlet, and the hydraulic efficiency. So here it's maybe a little bit confusing because the question asks us to calculate the minimum, the maximum hydraulic efficiency means there are no losses. But at the second paragraph, in the second paragraph here, it gives us the losses and so on and so forth. So how we could think about this. So actually, we must understand the meaning of hydraulic efficiency. So the hydraulic efficiency means the efficiency that occur at the blade, at the runner. So means that the maximum efficiency, the maximum efficiency for hydraulic efficiency means there are no losses when energy being absorbed at blade, at the runner. Okay, so this velocity, if you see the kv2 square over 2g and kv square over 2g, so you could find that this equation is actually similar with the minor losses in pipe system. So we learned about major loss and minor loss in fluid mechanics 1. So the equation for minor loss is kv square over 2g. So means that this equation is actually telling us about the whole situation. Means this is the turbine. So it's come from higher level. This is the outlet. So the major loss and minor loss that occur inside a pipe is this one. And then the 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 friction on the blade, the friction inside the turbine can be neglected because we assume that the minimum, the friction is low. That's why the hydraulic efficiency is maximum. So this is the situation in this question. Okay, so hydraulic efficiency can be determined as this one, as given in the question. When total loss is minimum, so the efficiency hydraulic will become maximum. So total loss can be written as this one. So define an expression for V equal to with maximum hydraulic efficiency. So in this question, the whirl velocity is not 0. So from the velocity triangle, so means that we need to draw like this one because the question asks to calculate the V equal to. So and then we could make a trigonometry here. So I think you already agree that V2 square is equal V2 square plus Vf square because we have this one. So we have the U2 here, V2 here. So and then we have V2 here and we have Vf2 here. So this is the triangle. So we could write the vector is like this one. So and then we have the VR2. So again, we have the VR2 here. So it is equal to Vf2 square. We have here, okay, this is the VR2. So we have Vf2 and we need to take this length. So this length is actually the U2 minus V2. Okay, so we try to substitute the value here. So because we maximum efficiency, the total losses is equal to 0. So we just equal this one with 0. And then we substitute the VR2 and V2 here with the term that we get from here. So we substitute with this one and we substitute with this one. Okay, why we need to substitute this term? Because the question asks about VWL2. So how we want to solve VWL2 if our equation didn't have any term for VWL2. So that's why we change the terms here with equation that have VWL2. So this is the equation. So and then to simplify the term, we differentiate the term with VWL2. So I think this is a quite common step in mathematics. Normally, if we have a curve like this, okay, why we assume curve in turbine or centrifugal pump is the quadratic curve like this one? Because as you know, in my lecture in centrifugal pump, sometimes if we increase the head, we increase the, I'm sorry, when we increase the flow rate and so on, the head is not linearly rise. It has a maximum point before it going down like this one. So that's why. And then if we differentiate it, means so we take the maximum one at this level. Because if you read the question carefully, we are aiming to get the maximum value of efficiency. So that's why we need to differentiate the terms. So I think this is a quite common method. If you have a quadratic here, so if we differentiate it with x and y, y to x, so and then dy dx, so we will get the maximum one, the maximum value. So this is the meaning of our differentiate process here. So we differentiate like this one, dhl over dwol2 equal to 0, and then we could have this term. So I think you could see we have this term first, so and then we differentiate it. So we will get this term, and then we could simplify it as this one. Okay, I hope you could try this at home. So we will have this term. So and then this is the terms for VWL2. So it means that when VWL2 is equal to this one, okay, so the hydraulic efficiency will become maximum. Why we could make this statement? Because we differentiate the equation. As I said, so if we have some graph like this, so we differentiate it, so we could get the highest peak, the highest amount, which is the maximum amount. Okay, and then we try, because here we have problem because we have K1 and K2, and we need to determine what is K1 and what is K2. So from the question, we know that the relative velocity, it is mentioned here in the question. Okay, the head loss of relative velocity is 5% and the draft tube loss is 20%. So the terms of 5% and 20% here is actually the value of K. So, so we assume that. So the relative velocity is 0.05 VR square over 2G, and draft tube is 0.2 V square over 2G. So how we know this one? So it's depend on the term. So as we see here, so we have the relative velocity. So the relative velocity means VR, and the draft tube here, as you know, if we have a turbine here, so the water comes in and water comes out. At the outlet here, we call it as draft tube. So this is draft tube. So at draft tube here, the water will flow as actual velocity. So means here is the V2. That's why in this equation, we assume that 0.05, which is 5%, it actually belongs to VR2, which is the relative velocity. And zero point 0.2 here, which is 20%, is belong to the draft tube. So the draft tube here is the actual velocity. So that's this is what you need to understand from this question. So and then if we have equation of this one, k VR2 square and so on and so forth. So k1 VR2 square over 2g plus k v2 square over 2g. So we substitute the value of k1 here as 0.05 and k2 here is 0.2. So we could calculate the value. And then we calculate the value. So from the equation, we could get the VF is 7.5 meter per second and the U2 is 15 meter per second. So please remember that the VF and U2 can be calculated from the equation. So we have this value. So and then we could calculate the world velocity at outlet, okay, at maximum efficiency. So means we are using equation that we get from the our differential process here. So it's V2 K1 over K1 plus K2. So we substitute the value. We substitute the value of U2 equal 15 meter per second. So the V2 is 3 meter per second. So this is the value of V at outlet. So and then the guide vane angle at outlet. So from the velocity triangle at outlet here. So this is the outlet. So and then the guide vane, as you say, normally people don't put guide vane at the outlet because it is outlet. So we just let the water goes out. Okay. However, if people start to if people ask about the guide vane at the outlet, so it is okay for you to take the angle of this one. So maybe this one. So the angle about the actual velocity. It is okay for you to take angle of this one or angle of this one. So let's say if I take the angle of this one, so the angle here is equal to tangent is VF2 divided by V2. So if we divide with the value, so it is 68.2 degree. Okay. So this is the Okay, this is 3 meter per second. So I'm sorry. So this is 3 meters per second. So I hope you could make correction of this value. But the equation is correct. Okay, so I hope you could do the correction here. So and then next, the blade angle at outlet. So the blade angle means the angle related to VR2. Okay, so this is the blade angle at the outlet. So let's say we determine the angle is here, beta 2. So we could calculate it by using the idea of tangent. So we have VF2 here divided by this length. So this length is U2 minus V2, like this one. So we substitute the value. So we could get it is 32 degree. And then the hydraulic efficiency. So the hydraulic efficiency from the question, the equation is given like this one. So we found that the height of the water level is 90 degree. So so we could calculate the value of HL here. So we just use the equation given in the question. So we substitute all the value of K, BR, and all of this. So we get it is 1.175 meter per second. So and then From the velocity triangle, I think you know where to find this one. So you just see the velocity triangle at the outlet here. Okay. So we could have the trigonometry equation like this. So it is equal to 225 meter per second if you substitute the value. So the K here is 0.02. So the V2 is 65.25. Okay, so mean we could substitute everything to this equation. Then you will get 1.175 meter per second. So, and then after we calculate that one, so we put everything here. So we substitute the value of losses is 1.175, and we get the height is 90 meters. So, and then we get the hydraulic efficiency is 0.987, which is 98.7%.